So let me begin. Hi, everyone. My name is Kang from Korea University. I will be presenting our research, modular component-based quantum circuit synthesis. This is a joint work with Hakjoo, also from Korea University. So as the title suggests, our research is about the synthesis of quantum circuits. So let me first introduce some concepts of it. Although the circuits are the lowest level of programs, we focus on the synthesizing circuits. This is because we believe that circuits are sufficient in the early days of quantum computing. So, for example, consider the Shor's integer factoring algorithm, which is one of the well-known applications of quantum computing, as it can be used for breaking the well-known RSA cryptos. It possesses a quantum complex structure and is in a non-trivial scale, and yet, just like this diagram shows, it is enough to be described by the circuits. So here's more detail in quantum circuits. Quantum circuits are composed in qubits, which is a quantum version of bits, and quantum gates. In this diagram, wires represent a physical placement of qubits, and some symbols on wires. For example, here a box state represents the quantum gate named Hadamard, and a vertical line that bridges two wires with some circles on it represents the gate named C0. And then its computation is basically a linear algebra. Each qubit holds its state value as a vector. For example, the symbol 00 cat, and often it is expressed in a cat. And for example, the symbol 00 cat represents the four-dimensional vector where the first element is 1 and the rest of elements are 0. Then naturally following, a quantum gate becomes a matrix transforming the state vectors. So for this example of circuit diagram, when input state vector is provided as 00 cat, this sequential quantum gate produces another state vector where 00 cat and 11 cat is proposed, which is evaluated to be the vector on the rightmost. And we found such quantum programming is hard. Indeed, this case of stack exchange question confirms the difficulty. The questioner asks for a circuit that maps 100 cat to a state vector where 30 cat and 31 cat is proposed, and the solution circuit turns out to be the right there. I guess it seems like a relatively simple circuit, but this case of question here shows that quantum programming is hard even for the simple cases. We figured that this is maybe because the linear algebraic nature of quantum computing, where the basic operations are matrix, which is definitely non-intuitive to the manual computation. So here, our basic goal becomes to give an automatic synthesis of quantum circuits for the programmers. And here's another example, which is even more non-trivial. Consider a synthesis of 3-qubit quantum-free transformation. It is a key part in many practical quantum algorithms, including the Shor's algorithm. And the input-output specification for QFT it should be given as this, which I guess is definitely non-trivial to program. And also, there were cases of question from circuit programmers asking for the implementation of QFT. This supports the difficulty of the problem. And indeed, actually, there already is a technique that produces a quantum circuit when I/O specification is provided. However, we would like to say such techniques are presented to be compilers rather as a means of generating only machine-readable circuit by fixed global level gates that only computer machine can directly process. So, for example, consider a gate named U3 and C0, which becomes one of the choices for such low-level gate sets. When the existing compilers is fed by I/O specification, for example, the I/O spec of 3-qubit QFT, the compiler gives a circuit, but barely compressive one, as it is inflexibly composed by a massive amount of low-level gate sets. So this fact gives one of the necessity of our problem, which is component-based quantum circuit synthesis. Basically, we assume user specifies input-output specification, and also we assume user specifies component gates that will be used as an ingredient in a circuit construction. Note that ours adopts the component gates to be any, so especially when specifying the component gate to be high level or something that reflects the programmer's mind, then our synthesizer produces a circuit written in component gates, which will be barely readable to the programmers, which is contrast to the result from the compilers appeared in the previous slide. And by the way, our technique successfully synthesized this QFT circuit in 220 seconds, while the baseline, which will be explained later, produced timeout. So here's our approach to the problem. Although the domain is new, we follow the typical method for the program synthesis, which is to do search-based. The most simplest method will be enumerating the space of quantum circuit by building up the circuits with component gates one by one. But for ours, we take a little variant version. Instead of enumeration by single gate operations, we conduct the enumeration by appending modules. Here for modules, it's a simple concept. We mean a collection of component gate operations. So for example, in this diagram, each orange boxed sub-circuit represents the module. And by this modular approach, we are taking a big step in each stage of synthesis and expect to reach the solution circuit in a faster step. But of course, our choice of this modular approach does not give inherent speed up in search. What's most important is the guidance of modules to append. And the method of guidance becomes our key idea in this research. Our idea is praised in saying, filling the attribute difference. So for explanation, consider I/O specification as pair of in-cat and out-cat. Especially, we color the out-cat as blue, and as our object is to prepare the out-cat, we can just simply say it as an object state vector. Here, SB is a short name of the state vector. And also, a green colored cat will represent the output state vector of some quantum circuit QC appear during the synthesis. Simply saying, since green cat represents the current status of a circuit under the construction, we can simply say as a current state vector. Then we characterize the difference in attribute level between those object state vector and the current state vector. Then we guide to append the module that fills the difference between them. So more concretely, if a module M transforms the current state vector to be same with the object state vector in an attribute level, then we append the M. So, and in contrast, for another module M prime, if it does not transform the current state vector to be same with the object state vector in attribute, we prune out the M prime. So we will dive into the simple working example that shows how our idea applies. Consider an example where the goal is to synthesize a circuit that maps 1, 0, 0 cat and to another state vector where 3, 0 cats and 3, 1 cat is proposed. The specified components gate is H and C naught, which means that we will be appending some modules that is composed by H and C naught. Initially, the synthesis starts off with the blank circuit, and its action is identity function, mapping the input 001 cat, the 100 cat to 100 cat, the same one. For the blue-colored object state vector, through the calculation, we can check that object state vector is entangled. Here, entangled is some terminology in quantum physics, but mathematically, we can understand it as inseparability by tensor products. And in contrast, output state vector of a current quantum circuit is an entangled. Hereby, we derive the attribute difference between them as an entanglement. Then our guidance goal becomes to append the module that fills the entanglement difference. We prepare the candidate modules for one that is likely to fill the current entanglement difference, although the detailed method will be skipped for now. But anyway, let's see how each module transforms the current state vector and decide which to append. The M1 prime module gives a state vector which is not entangled. So we can say that M1 prime does not fill the entanglement gap. So we decide not to append the M1 prime to pruning out it. And in contrast, the M1 module transforms the current state vector to be entangled, being same as the object state vector in attribute. So as we can say, M1 fills the difference of entanglement. We append the M1 in the synthesis. So as a next stage, we may start the synthesis from the circuit with M1 appended, obtained from the previous stage. So in this stage, considering the action of the current circuit, we can check that current state vector is different in sign of coefficient compared to the object state vector. And by some quantum basis reason, we call it as a difference in relative pace, or shortly just a pace. Then the guidance will become to a append a module that fills the phase difference. And also in this case, we prepare the modules that is likely to fill the phase difference, such as M2 and M2 prime. But here, M2 actually switches the minus sign to the plus sign, thereby reaching to the object state vector. So just by coincidence, we may get to the solution circuit before the pruning modules. So far, this was all about our method for the guidance. Now we will convey to the evaluation result of our synthesis algorithm. We prepare 17 non-trivial synthesis problems from sources like textbooks and stacking questions in the internet. And we give 2 other settings as major comparison target. We set the baseline as the most naive approach, which is to enumerate by gate operation, explained just ago. And also, to check the effectiveness in guidance, we also compare with the modular approach. We also compare with our modular approach without the difference filling guidance. So here's a table. In overall, our approach could achieve effectiveness compared to other 2 settings. First, while the 2 other settings solved 10 and 14 problems out of 17, ours could solve 16 problems within time. So also in terms of speed, ours could achieve faster synthesis time. Compared to the baseline, in average, ours achieved 6.6 times faster in synthesis time. And compared to ours no prune, which is our version of no guidance, we achieved a 7.1 faster synthesis time, which implies that our guidance filling idea was effective enough. And also, here we show the result of a circuit presentation by our component space and the one from the existing technique, which is to be a compiler. Since the component gate was specified to be enough high level, we could achieve pretty neat representations, while by the compiler tool, it only managed to produce the incomprehensible one. So again, this supports the value of component-based synthesis. So actually, here's the summary. Here's the summary. We proposed a problem to synthesize a circuit with I/O specification, and the user provided component gates. We took a search-based approach, and our key idea was to characterize the attribute difference and guide to append modules that fill such attribute difference. And personally, more importantly, several features works are established from this study. The most direct feature work will be extending our work to a language-based quantum programming, which is written in, for example, the Silk, and the Qiskit, which is embedded in the Python. And also, we can apply our synthesis idea to other synthesis problems, for example, circuit optimization. So this is it, and thank you for listening.
Hi, thanks for your nice talk. The input-output specification, do you only specify one in and output, or can you also specify multiple ones?
There is some limitation. It could be one or multiple, but only through the explanation. Only in the working example, I suppose there is one single I/O specification.
Yeah, that's why I ask. I assumed that already. But when you have different in and output pairs, you could have different attributes.
Okay, that's true. Yeah, that's
and
true.
How do you choose between them? Do you have some heuristic or?
I managed to have a board so of course if there is a multiple I/O specification, there could be multiple kinds of attribute differences. But I chose one of the most frequent differences as just a simple heuristic. But yeah, that's a simple heuristic. But anyway, it works. So
thanks.
So I have one question. So it seems like you expect the user to give you the components.
Yes.
Right? And is that easy in practice, or are there? Did you ever face any issues with?
Well, I like to say it can be easy, but in practice, at least not for every problem of synthesis, it may not be easy. So actually, this becomes one of the future directions that we have to resolve. For example, assuming that component gates include something that is not proper. So, yeah, that remains as an issue in this research.
And what is the largest circuit that you were able to generate?
In terms of qubit size, the largest one was actually 4. I know it's a little bit disappointingly small, but yeah, it's small, but I guess it may be practical enough for the early days of quantum computer, because still in this early days of quantum computing, the perfect qubits are only about 7, or only about the 3 or 4 qubits. So yeah, but still we have to resolve the scalability. Yes.
Thanks. Other questions? All right, well, let's thank the speaker one more time.